They can see it. All right, we are recording our last class kind of session of the semester. I'm going to go ahead and share screen here. Josh, do you mind making sure people get in? We'll hear a little bing to make sure that we know they're coming, but thank you. All right, so let's start out with, we're doing clicker questions tonight. They're not included in the participation grade for the course. That is already done. I think almost everyone got full credit on participation. So that is a very exciting thing. It means you got over 85%. And if you did not, and you're right below the cutoff for that, and it was because you're sick or you're traveling for a team or something like that, and your grade cutoff, like you're at a 79.5 or something like that, then email me and I'll look at the whole picture. And then if that's what's keeping you from having that letter grade, I'll reconsider depending on the circumstances. So let's go ahead and start by having everyone shake off the nerves, shake off the exam 3. Hopefully a good number of you have completed that. I've heard that people, the average time to complete has been about an hour and a half. That's for the OWL part. And then the other part, I don't know what the timing is. What would you estimate? 20 minutes? Does that sound reasonable for the OWL, the Google Forms part? About. So make sure you plan ahead and have enough time if you haven't completed that yet. For exam 4, I did have a couple of comments about what we wanted to work on for this last review session. And so that's kind of guided some of my putting stuff together here. If there are topics you want to work on that are not in this review session, please feel free to come to my office hours. I have them, tomorrow at like, I think there's one midday or morning, and then one in the evening at 8 p.m. And then on Wednesday, I have some as well. So there's still plenty of time to meet and have review sessions. Can I just get a show of hands? Will anyone actually show up to the 8 p.m. review session tomorrow night? Okay, we have at least one, potentially 2. All right, that's enough for me to hold it. I just don't want to be sitting there by myself and like block out dinner and then sit there by myself. I'd be happy to do it for you guys. Okay, so go ahead and draw. We're going to shake off the cobwebs. We're going to remember stuff from the beginning of the semester. So go ahead and draw these Lewis structures, which will mean you need to remember your polyatomic ions. Do you want to do breakout rooms for this? So you can bounce it off each other? I see some shaking yes, some shaking no. We're going to go ahead and do that just for a few minutes. If I can get my computer to let me. We'll do breakout rooms for about 2 minutes. All right, I'm gonna go ahead and start that now. All right, so as you probably have noticed, this isn't really a clicker question. I just sent it out so that you all have the question. Also, if you've noticed, there is the worksheet for tonight that has all the questions in it. And you can access and download it. It was uploaded a bit late, so that might be why some of you might not have already seen that. You will also notice that tonight's class will be doing moving pretty quickly, I'd say, through a lot of these, because the point of tonight's class is not to say, here's how you do this. It's, hey, remember, this is a topic we did a long time ago. Make sure you know how to do this for the final exam. Is that fair? So this one, I probably gave you more time than I meant to. So we'll go through the steps really quickly, and then you can mark this off as, oh, that's something I really need to go back and study, or that's something I got, we're good. So can I hear from Sydney Chastain, who was in my group? What are the steps kind of we need to do in order to draw the Lewis structure for perchlorate, at least the first few?
So we made a point to realize that it has a -1 charge.
And what's the formula?
ClO4 minus.
Great. So ClO4 minus perchlorate, we need to remember all of our polyatomic ions. Once we have that, let's see if my pen will write. Hopefully it will. And for some reason it's not. I'll do it with my finger. This is going to be ugly. Sorry. So we have ClO4 negative. That means we have 4 oxygens. We can figure out our total valence electrons. And how many valence electrons did we calculate, Sydney?
32.
And then the question is just where we put those. So the equation that we use is S equals N minus H. So in order to find the number of shared electrons, we can take how many electrons we need if everything had a full octet, subtract out how many valence electrons we have. And we're going to find that we have 18 shared electrons, because we would need 5 elements times 8 electrons each. So that would be 5 times 8 is 40 minus the 32. I totally screwed that up. So if we did it this way, we would find that we had 8 shared electrons. But then what happens is if we draw, oops, I don't know what I'm doing. If we draw a perchlorate like this, we're going to have a ton of electrons in lone pairs. We're going to have a lot of negative charges and a lot of positive charges. So this equation, S equals N minus H, is a great starting point if we have something that obeys the octet rule. Does chlorine have to obey the octet rule? So remember, anything that's in group 3, or sorry, period 3 or lower does not have to obey the octet rule. So we can go ahead and make double bonds to the chlorine. That was a bad last electron. And if we do that, we will have 1 negative charge and a whole bunch of electrons. We'd have to go through and count, make sure all the valence electrons are right. And so if we count here, we have a total of 1, 2, 3, 4, 5, 6, 7 bonds. So that's 14 bonding electrons. We have a total of 3 times 4, 12, 13, 14, 15, 16, 17, 18 bonding electrons. 18 plus 14 is 32. So we have the same, we have the right total number of electrons. So the most critical thing is to make sure that we count for all our electrons. One of the things I told you back this part of the semester is to memorize your polyatomic ions. And when you do that, make sure that you go in and also just look up the Lewis structures for them or try drawing them. That's going to be really good practice for learning to do Lewis structures, especially with things that don't obey the octet rule. Okay. What about ozone? Ozone's going to be a bit easier because oxygen is in period 2. Oxygen has to obey the octet rule. So we have our formula is O3. How many valence electrons do we have there?
18.
So we have 18 electrons because each oxygen has 6 valence electrons. We have 3 of them. We have 18 total electrons. And then we try drawing our oxygens connecting to each other. If we do the S equals N minus H, it's actually really useful for this molecule because everything obeys the octet rule. So to find the number of shared electrons, we have to do if everything had a full octet, we would have a total of 8 electrons for each of the 3 atoms. That gives us 24 electrons. We know that we have 18 electrons, so that means the shared electrons is going to be 6. How many bonds can we make with 6 shared electrons? 3, right? So this molecule has 3 bonds or 6 shared electrons. But we have a total of 18 electrons, so we're not at 18 yet. So we've counted for 6. We have 12 more to go. So we can go ahead and add those to the molecule. So I've added another 8 electrons. We still have 4 more to go. We can't exceed the octet rule. We have to obey the octet rule because it's in period 2. So the central oxygen still needs 2 electrons in order to get to that octet. Far right one needs 2 more electrons to get to that octet. So then with that, we'd have to say, well, we could then ask, remember, these are the questions that I would ask you on a Lewis structure. What is the electron geometry at any atom? Basically, where are those domains of electrons around it? What is the molecular shape? Meaning once you have accounted for where all the domains of electrons are, where are the electron domains, the bonds specifically in space? So if we looked at this central oxygen right here, would anyone like to take a chance and answer what our electron geometry is and what our molecular shape is around that oxygen?
Would it be bent?
Which one? Molecular shape or electron geometry, or both?
Molecular.
What would the electron geometry be then?
Wouldn't it be trigonal planar?
Why?
Because it has 3 domains in the center atom.
Great. Sorry, my writing is terrible. I don't know why my pencil's not working today. So that central oxygen has 2 bonding domains, a single bond and a double bond, and it has a lone pair. So 3 domains means trigonal planar. That's how far they can get spread away from each other without interfering with each other. But then the atoms, out of those 3 domains, it makes a Y, right? 120 degrees from each other. 2 of those are bonding domains. And so those 2 we describe as just being bent. This is linear, this is bent. So I agree with Kat and Taylor. Okay, so if that doesn't seem super easy to do, or you're really refreshed, you are going to be asked to do that in the final exam. So make sure to brush up on how to draw Lewis structures. And then we could say, are there any polar bonds in the molecule? If so, do they cancel each other out? These kinds of things. So we are, don't worry about the clicker. Like I said, we're not counting clickers at all tonight. I'm just using it as a tool to make sure we stay engaged and I hear from all of you. I will shift gears a little bit and do some logistics. If you look in Blackboard right now, you will see your exam 3 score if you've completed it by, I'd say 5 p.m. I've gone in there and graded a couple of those. So I've put the complete score. If you see an exam 3 score in Blackboard, that is your exam 3 score. I've also taken your OWL scores, and if you went to workshop, I've used that as portion of your OWL and workshop score. It can only improve your grade. It will not decrease your grade going to workshop. And the number of them increased your grade by a certain amount. So that has already been factored in OWL. The only time that that grade will change now is if you have not yet completed those 2 surveys that are going to factor into your post-quiz category. So if you're, well, any way you look at it, please complete those surveys. It is really valuable data for me to learn how I've impacted your learning and your perception across the semester. And it also is part of your OWL grade. Your iClickers have also been incorporated. Once again, if you are using the grade estimator to think about what you can do in the final exam, use the raw score. That does then calculate your final score, which you'll see off to the right of the raw score. So it does include that, and that's what the weighted grade in your course does include, is the final iClicker, which is out of 85%, what is your score? Lab grades are up in final. Those have been provided by Peter and Humendra, so those are in there. So the only thing really left is if you haven't completed the surveys, if you haven't completed exam 3, and your final exam. Any questions about grades that are up right now or other components of the course? Nope. Okay, feel free to stay after class if you have any more questions, either logistics or concepts, by the way. I'll be happy to stick around for a while. All right, so let's try to do another Lewis structure type question talking about polarity. We're going to do a few of these, and you'll see that in the worksheet if you haven't downloaded that yet. So I want you to take a look at this molecule, decide whether it's polar or not, and that's going to involve a few steps. Can I get a thumbs up, thumbs down? Would you like to go to breakout rooms for this? Thumbs up for breakout rooms. Okay, I saw 5 thumbs, 4 were down, 1 was up. So we'll stay out of breakout rooms, and we'll spend about a minute of you trying to work this out. Be as specific and detailed as you can on your own paper. Try to write out how you would answer this question. Don't just guess. All right, we got 7 clicked responses. So if you have an idea, go ahead and submit that. Okay, we're up to 11. 14. All right. I would love, love, love to hear how we approach answering this question. Can I have a new volunteer? We've heard from Taylor and Kat, and I think that might be it in the big group. So can I have someone else volunteer to talk through how you might answer this question? Carter, is that you raising your hand?
Yeah. First off, you gotta know what the difference between polar and non-polar is. And then when you got that down, you just gotta figure out what the electron geometry of it is, and then you can figure out if it's in the polar, non-polar after that.
So what is the difference between polar and non-polar?
Basically well, we talked about it a lot at the beginning of the semester, but for example, like hydrogen is polar, CO2 is non-polar. It's just like a linear bond, for example, is linear bond would be non-polar.
Okay, so I'm going to take a couple things you said there and separate them and be very specific. A hydrogen atom may or may not be polar. It totally depends what it's bonded to. So I like the part you said, well, it's about the bond. So a polar bond is something where you have 2 atoms that are bonded to each other. Sorry. Get not white pen. If you have 2 things bonded to each other, if they are the same electronegativity, it's all about the electronegativity value of those atoms. If they're the same electronegativity, doesn't matter how different they look. If they're the same value, then there's no polarity. So we could have hydrogen bonded to hydrogen. That's a nonpolar bond. We could have carbon bonded to hydrogen. Their electronegativity values, or the pull they have on electrons in a bond, is very little. But if we have a hydrogen bonded to an oxygen, their electronegativity values are very different. So what about chlorine and carbon? Is that a polar bond? What do we think? Yes, polar? No. So I think the answer is yes. I think the electronegativity value of chlorine is a little bit higher than carbon. So I would say that carbon-chlorine bonds are polar. So the first question that we always ask is, are there any polar bonds in the molecule? If the answer is no, then we're done. It doesn't matter what shape it is. It doesn't matter what's connected to what. If none of those bonds could potentially be polar, we're done. There is no polarity. It is a nonpolar molecule. In this one, we say, yes, there are some polar bonds in this molecule. Then we have to go to the next step, what Carter said, and we have to think about what is the three-dimensional structure of that molecule. And so that means we have to think about what the Lewis structure would look like. So here is a drawing of the Lewis structure for this molecule. I want you to go ahead and revote. It's still open. Go ahead and revote. I'm going to give you 20 seconds to revote whether this is polar or whether this is nonpolar, now that you have the structure and we know that there is a polar bond in the molecule, or two polar bonds. Couple more seconds. Okay, so we had a shift in answers towards answer A, that it is nonpolar. Can I have someone change their answer towards that? Tell us why.
So I changed mine just because it looks symmetrical.
Why does that matter?
I'm not too sure. It's not polar, like it doesn't pull on one side more than the other.
Okay, so what you're getting at is that we have dipoles that we can draw that show what directions in a bond those electrons are being pulled. And if that pull is completely symmetrical around a central atom, then we can say it's nonpolar. There's one caveat though in this question that we're forgetting, and it's exaggerated by the way I drew it. So I did this on purpose. What's to say that I couldn't have drawn the chlorine up here? That I couldn't have drawn both the chlorines at the top, in which case it wouldn't be symmetric anymore. So we have to remember that this central bond, a single bond between two carbon atoms, spins completely freely. If this was a double bond, then we would say, oh, that can't rotate anymore, and we can't, now it's fixed in space. But because it's a single bond, both sides of that are completely free to spin, and only in a very specific configuration where they're pointing opposite directions from each other is that nonpolar. So we have to say, are there polar bonds? Where are they in space? And are they stuck at a position where they would cancel each other out? So this was a little bit of a tricky question, but this molecule is polar. So this is a false statement. And the reason it's polar is because this is not the only way that this is drawn. And this isn't even a three-dimensional drawing, right? This is a two-dimensional drawing. So each one of these carbons has a tetrahedral molecular shape, which means that those chlorines could be sticking both up. And if they're doing that, those dipoles don't cancel each other out. So symmetry is important, but it's most important around a single atom. And if you have a larger molecule with rotating bonds, it's probably more common just to say, are there polar bonds in the molecule? If so, then there's polarity. If there's no polar bonds, there's no polarity. All right, let's do a target here. Let's say that we have this molecule, salicylic acid, and we want to put it in water. Question is, which hydrogen atoms can form a hydrogen bond with water? And click on, you only have one click unfortunately, but click on any one that you think would form a hydrogen bond with water. You want 60 seconds in breakout room for this? See head shaking. Okay, I only have 5 responses. Make sure you hit send after you click on the part of the screen that you think applies. I only have 9 submissions. I'll give another 10 seconds. So now the question is whether I can share the screen with you all. Let me try to share, new share, see if it'll let me. Let's try that. Okay, can you see the responses to the clicker? Oh, you can see the screen, okay. So we have, someone changed their answer. All right, so we have 12 responses right now that are focused on 2 hydrogens. They're focused on this hydrogen out the far right side, and they're focused on the hydrogen down at the bottom. Someone selected this hydrogen out here on the left side at first. Why is that not an appropriate answer for something that can hydrogen bond with water? Why is this hydrogen not appropriate?
Bonded to either fluorine, nitrogen, or oxygen.
Sorry, can you speak up a little bit? It's hard to hear you.
It needs to be bonded to either fluorine, nitrogen, or oxygen.
Why does it have to be bonded? Why does a hydrogen atom have to be bonded to fluorine, oxygen, or nitrogen in order to participate in a hydrogen bond? If we go back to our definition about what a polar bond is, why is that so important to have the hydrogen connected to an oxygen, nitrogen, or fluorine?
Is it because they're the only ones that can form hydrogen bonds?
Yeah, it's kind of defining it by its own definition, though. Looks like there is a chat response. Because hydrogen bonding is fun, true. Why? Why does it matter? What's a bigger category hydrogen bonding falls into?
An IMF, right?
It's an intermolecular force. So it's 2 molecules that are interacting with each other. So why is the hydrogen on one of them need to be connected to an oxygen? What's special now about that hydrogen to oxygen or fluorine or nitrogen bond?
Is it because they're polar?
Because being connected to a highly electronegative atom, hydrogen connected to that atom is now polar. So if we look at this bond here, those electrons are being pulled very strongly in the direction of that oxygen. We can draw a dipole there. In this bond over here, the electrons are being shared pretty equally, and so there's no dipole. So remember, the bigger category is dipole interacting with a dipole. That's the type of IMF that we're always looking for. If there's no dipole in a bond, remember, it's always about the 2 atoms sharing those electrons, and if they're shared equally, there's no dipole, nonpolar. So if it's a dipole, then the question is it the strongest of the dipole-dipole interactions? And if an oxygen is connected to a hydrogen, that means that hydrogen is very electropositive, partially positive. It's about 1/10 or 2/10 of a positive charge. And that oxygen then is partially negative, about 1/10 or 2/10 of a negative charge. It's not as charged as an ion, but it's moving in that direction. So without that partial charge, you're not going to have that strong. Because if you have 2 molecules that are moving past each other, why are they going to be attracted? You have to have a little bit of electrostatic interaction in order to have that intermolecular force that Berto was talking about. And that intermolecular force comes from, think about a balloon sticking to your hair, right? There has to be a little bit of charge difference between the 2, and that will pull them together. And that's what makes interaction between water, and in this case, that partially positive hydrogen. And that electrostatic interaction is not a new chemical bond, but allows them to pull together and be more attracted to each other. Questions on that? As we're going through this, I want you to ask questions. Or just quietly stare at me. That works too. Cool. All right, let's do a compare of these two. So I am going to send you to breakout rooms now. I want you to tell me which of these two molecules is most water soluble. And I think I'm going to send. All right, go. Good. Sydney, you found a problem with my setup of the exam. I appreciate that. Sydney Chastain, that is.
I'm just glad you noticed it.
I didn't realize that I originally had it set up so you couldn't take part 2 without taking part 1, but then somehow when I renamed part 1, it like broke that link. So you were able to bypass it. All right, we have for once a uniform decision. So Ms. Gamble, would you mind sharing your description of how you would choose which one of these is more water soluble and why?
Sure. So I chose B, the solicit. I can't say it. But I chose B because the ratio of nonpolar bonds to polar bonds is smaller than the methyl salicylate. Which means that water has more opportunity to surround the molecule versus the methyl molecule.
Fantastic. So it's about how many polar bonds are there? What's the ratio of polar to nonpolar bonds? And then that will dictate whether that can be saturated by water being around it. And we talked in our group about the difference between dissolving and breaking apart. When we say break apart, a lot of times that means the bonds between the atoms will break, and that's not at all what's happening. We're dissolving it, we're covering each molecule in water as much as it can, and that's what dissolving looks like. Okay. And we didn't have 100% of the votes in, so maybe I lied because I said we had 100% agreement, but we were missing 2 votes. All right. So along the same lines, as we clear up properties, we're going to try to do this one relatively quickly. I'm going to give you all 1 minute and 30 seconds to answer this question. Which of the following solutions would have the least depression of freezing point? And maybe we'll do a minute in the breakout room. So if you have a question or want to talk about it, you can. I'll close it in 30 seconds. Stay put, Tracy. All right, y'all, 12 responses. Is this bringing up some topics we might need to go study? Is that what this is telling me? Because it's an equal distribution basically between all 3. So when we were in our small group, Danielle said something that really is what we need to do to get started. She said that the more solute you have dissolved in solution, the more the freezing point goes down. So then the question is, which one has more solute in it? And remember, the definition of amount is the number of particles. So if something goes into water and it stays intact, like glucose, one thing in equals one thing in water. Is that true for ammonium hydroxide? What happens when one ammonium hydroxide goes in water?
It breaks apart into 2 molecules.
Yeah, actually there are molecules. So 2 particles also be the way to talk about it here. So NH4OH. So remember this term, the Van't Hoff factor. So every 1 breaks into 2. So the actual concentration of solutes in solution is 2.50 for this compound. Does glucose break into particles? Are there any ionic bonds in glucose? Nope, Van Hoff factor is 1. What about calcium hydroxide?
3 particles.
Okay. And then we would do the calculation and we'd see which one of these has the lowest number after you figured out the molarity of ions in solution. And I think that the one that's lowest is, what is it? 7.5? I think it's C, is that right? If I do my math right, it's 1.575 molarity of particles in solution. Which would mean that one changes freezing point the least because it has the least concentration of particles in solution. Okay, I'm looking at the clock here and getting a little worried. We have people that are, I can't tell if you guys are just not comfortable with the topics, haven't got a chance to review them yet. If you're just really quiet, some of you have taken the exam today, so you're maybe a little bit tired, but I'm gonna try to pick up the pace a little bit, all right? So let's take a look at our next question. If you have a chemical reaction that is 2A plus 5B gives 3C, all right, some DS reaction. If we can measure the rate at which B is being consumed at a specific point in the reaction, and it's 350 millimolar per second, then what is the rate of the reaction? I'm going to give you 45 seconds to answer this question. We'll stop actually right at 1 minute on the clicker. Couple more seconds. All right, I'm gonna go ahead and close this out. And we have an overwhelming answer that is C. And for the sake of time, I'm gonna just use the phrasing that B is being consumed 5 times the rate of reaction. That's the way I want you to think about this, that the rate of reaction is as if something had a stoichiometric coefficient of 1. In this case, we don't have one with 1. So B is being consumed 5 times the rate of reaction. So if we divide the rate of consumption of B by 5, we'll get 70 millimolarity per second. That's the rate of reaction. So then with that knowledge, how do we feel about answering our next question? We'll do just a couple of seconds, use the same answers as above. Just a couple more seconds. We know the rate of reaction is C, 70 millimolarity per second. What's the rate of production of C? Closing out. All right, fantastic. Almost everyone answered E. And the way I like to think about that is C is produced 3 times rate of reaction. So that's 70 millimolar times 3 is 210 millimolar per second. So really what we're talking about is anytime you're trying to compare how fast something's being used up to how fast something's being produced or used up, we always think about what's the rate of reaction. And then once we find that, we can multiply that out. All right. Here's a conceptual question. We're going to run a chemical reaction. It's a decomposition reaction. It means that something's fallen apart. And we're going to run this reaction 2 times to see how fast the reactant decomposes. So what is the rate order if we find that the rate of decomposition is the same regardless of how much of the reactant we start with?
Would it be 0 order?
Why do you think it's 0 order, Stacy?
Whenever something's 0 order, doesn't it normally like not really affect the rate of reaction no matter what the concentration is?
Exactly. So our definition of 0 order is that the rate of the reaction is proportional to a rate constant. I guess you could say times concentration of the reactant raised to the 0 power, but that's just 1. So the definition of 0 order is the rate of the reaction is the same regardless of what our initial concentration is. So then what's our definition of first order? Sorry, I'm not trying to circle that as that's the right answer. Answer is 0 order. What's our definition for a first order reactant? How would we define that? Anyone want to take a try? Not clear or don't want to answer? How do we define first order or second order reaction? What does that mean about the reactant? One person answers, we'll move on.
Is this the one that's proportional to the change in
Which one
concentration?
is?
First order? What?
So if a reaction is first order, it means that as the concentration changes, the rate of the reaction changes to the same proportion. So it's proportion to the first power. If it's second order, it means the rate of the reaction changes proportional to a square of the concentration change. So that's really what 0 first and second order mean. So my next question is, why do we care? Looks like we had a chat response to that. So we'll come back to that. The question is, why do we care what the order is for a reactant? What does that allow us to do? I'm gonna have you all do 1 minute breakout, and I am going to cold call the answer after this. So please make sure your group has an answer that you're comfortable with. Why do we care? So you just like nailed it and like bounced back to the main group. Still? You can't hear me? I'm pretty sure my thing's not muted.
You talking to me, Professor?
I was.
Oh. I don't know if I nailed it, but I think I just got an answer for you if you need it.
Sounds good. All right, a couple more seconds for everyone's back. And I just did the target just so we'd have something so you could see it on your screens. All right, I think that's everybody. So I want to hear from Aislinn what her group talked about. Why do we care? Figure out what the rate order is for a reactant.
We weren't really sure. And we lost our person. Tripty wasn't there. So we said something about the time that it takes for it to occur.
We'll expand on that a little bit.
Like just how long it takes. I don't know.
How long what takes?
The reactants to produce the products.
Okay, that seems reasonable. Can I have Gabby, were you in the same group or a different group?
Same group.
Do you want to expand on that?
That's about as much as I knew also.
All right, Sydney Chastain, can you add in what your group talked about?
We mentioned pretty much the same thing around like the speed of the reaction.
Around what? Sorry, it's hard to hear you.
The speed of the reaction.
Okay, so if we know the rate order, then we can say the rate of reaction is proportional to the concentration raised to whatever power, right? Concentration of a reactant or multiple reactants. True. Aislinn, I think, was talking about, and Gabby was a little bit different. And they're saying that if we know our initial concentration, yeah,
We can't see your screen.
that would be useful. Thank you. Now, can you see my screen?
Yep.
I think I'd get used to this by now. All right. Come on, buddy. So if we know the rate order, we know how the rate of reaction changes related to the concentration of reactant. That's what we just heard a second ago. But then the next component of that Aislinn was saying is, what if we know our initial concentration? Then after a certain amount of time, what is our final concentration? That question is something we cannot answer until we know what the rate order of the reaction is. If it's a zero order reaction, we know that that change is proportional to time, and it's directly proportional. If we have our, Josh, can you get Tripty? I hope that's her coming back in, sweet. If we instead have a first order reaction, then it's proportional, as I think Sydney McMahon said in the chat window, the way that the concentration changes proportional to the natural log. If it's a second order reaction, concentration changes proportional to the inverse 1/. And so that's all about using calculus to derive the rate of change and how the concentration changes over time. So it's a derivative of the change in concentration. So without that, we could not answer a question like this. So here's a question that says, how long does it take if we have a second order reactant to decrease in concentration from 75.9 millimolar to 10 millimolar? And we have our rate constant. So which one of these equations would be useful if we have a second order reactant? And by the way, all these questions that I'm doing conceptual, work on your own. and actually find a numeric value and then see if that number makes sense to you. If you have time in class, or if not, as a study tool. Couple more seconds. And if this is making you feel like you got some cobwebs around this, that's the goal, is to hopefully have you identify what you do need to work on. All right, going ahead and closing out. So we're split between two answers. The two answers are A and D. One of the things I want you to think about here is, if we're looking for how long does it take, does D have time anywhere in the equation? Okay, so always look for the variable that you want to solve for in an equation. So all of the ones above here, these three all have time in the equation, but the one that applies for second order is this top equation. This one is 0 order, and this is first order. The bottom one is only useful if we want to know what is the rate of change of a concentration at a specific concentration. So only the relationship between concentration and rate. There's no time, right? All these T's that are in here, if we know the rate order, we can choose which one of those equations to use. And then we can solve for our initial, right? That's the one with the little 0, that means initial. So that's concentration initial. This is our final concentration, which is concentration at time t, or sometimes you'll see it as I for initial and F as final. So make sure not only that you know which equation to use, but that you can actually solve for one of the unknowns, because if you're solving for the concentration at time t, you have to make sure that you multiply everything out appropriately in order to get that A at time t by itself. So go back if you haven't already done so. If this seems like something you might struggle with, and it was something that people struggled mathematically with, go back and practice those homework assignments. Maybe this is a good time to show where we have some resources. We're kind of at the last section, but I'm going to stop sharing that screen for a second. And I'm going to share another screen here in OWL. So one of the resources that I think is extremely valuable for you all is the study resources, the adaptive study tools. Actually, I realize it's going to take me a couple seconds to pull that up. So what I'm going to do first is I'm going to send you into breakout rooms, and after this question, then we'll go ahead and we will look at those resources. So what I'm going to do right now is send you into breakout rooms with the question I just sent out. Breakout rooms, go. Hi, y'all. Looks like we have almost everyone back, except did we lose Tripty again? Or is she back here? She's here.
Yeah, I wasn't able to go to my breakout room because Zoom kicked me out again.
I tried to reassign you to that room. Sorry, Tripty's group. Okay, so we have a mix of answers. This is one of the most critical parts of the last third of the semester is what is it that we're looking at? So for this particular problem, how do we determine whether we take the negative log or we do an ice table or we do an ice table and then we take 14 minus the negative log of that? Can I hear from Patrick? What did your group discuss and what did you decide?
We discussed about it, but I'm still not sure. I think we went with C in our group.
Okay, do you want to talk through that at all?
I'm not really sure how to do it at all.
Okay. Can I hear from Tina? Can you elaborate on maybe what you and your group did? I'm not sure if it's the same group.
No, I was in a different group. We picked option C because we have chloric acid, so we chose to do the ice table.
Why? Just start on that step. Why did you choose the ice table? Why wouldn't we just do the negative log of the concentration? When is the only time we do the negative log of the concentration of an acid?
If it's a strong acid,
Sorry?
Yep.
it'll dissociate completely.
So Tracy was saying if it's a strong acid, then we take the negative log of the concentration. Chloric acid is ClO3 or HClO3. So it's not HCl or perchloric acid. Both of those are strong acids. So this one is specifically a weak acid. So that's the ultimate first step is this a weak acid or a strong acid, a weak base or a strong base? Yes. So we have to pick that first. So chloric acid is a weak acid. So we cannot just take the negative log. And it's really important too that we say it's an acid and not a base. So then we have to take an ice table to find our X value. The question is when we do negative log of that X, what is that? So Sydney Chastain, what is the X that we're taking the negative log of in an ice table for this problem?
Since we're given an acid concentration, it's our hydronium.
Fantastic. So every time you think about doing an ice table, think about what is my X I'm solving for represent. And in this case, it's the H+ ion or hydronium ion concentration. So we take the negative log of that, it's the pH. If we say, well, it's a base, so what we're finding is actually the OH- concentration, that's when we have to use answer C. So it's really important you do that first step and you do it properly. So I agree with the people who answered B. Pretty straightforward. Why can't we use a Henderson-Hasselbalch?
We don't have two different concentrations.
Keep going. What would it have to be two concentrations of?
Either it would either be the acid conjugate base or base and conjugate acid. Great. Or you'd have to there's another version of it that I worked through on the practice questions.
Yeah, so if you make a mixture of a weak acid, weak base, conjugate acid, conjugate base pair through a titration or a buffer, making of a buffer, that's the other way. Okay, so yes.
Sorry, so there was a little bit of confusion in our group. So it is actually B?
Yes, this is a weak acid in water. Yes. So we need an ice table to find X, which is a concentration of H+, and then we take the negative log of that.
H+. Okay, yeah, that
so in our ice table, do we use Ka or Kb if we had both of them in this specific problem? 10 seconds.
We use Ka. Sorry, oops.
So it's a question at the bottom. Are we using Ka or Kb in that ice table if we had access to both? A couple more seconds. And closing out. So majority of the class answered A, and that's because we have a weak acid. We're putting a weak acid in water. The question is, how much does it disassociate? So Amber had a point that she wanted to add, that chloric acid is sometimes referred to as the 7th strong acid. I'd say it's about 60-40, whether people call it a strong or a weak acid. The Ka value is relatively small, and so I usually go ahead and call it a weak acid. If you can look up a Ka value and it's not like hundreds or thousands, then we usually call it a weak acid. But that's a good point. You will sometimes see it as both. Okay, I'm looking at the time. We're at 7:10. Let's do the same exact type of question here. Let's look at a solution of hydrobromic acid. We have the concentration. Which approach would you use? Couple more seconds. And closing out. Okay, so for the purpose of diagnosing whether you're comfortable with this or not, I think that this is a relatively decent question. So HBr is a strong acid. So this means that maybe you're not comfortable with your 6 strong acids. Make sure you have those memorized. I can't say it enough. And then once you have that, you know you can take the negative log of the concentration and find the pH of that solution. What if we had this solution instead? And we're going to do 30 seconds on this question. We're not completely sure, but the majority answer that's winning out is C. Can I have, let's have Stacy. Can you explain why someone might pick the answer C?
I thought that potassium citrate would be basic in solution. So you would,
Why would you
or at
say
least
that?
When you separate potassium citrate into ions, you get the potassium ion and the citrate ion, and potassium's neutral in solution. So I just guessed that the citrate would be basic.
Okay, great. And maybe you've heard of, not you, but the whole class have heard of citric acid. So citrate is the conjugate base of citric acid. So that's always a clue, is if you can put acid at the end of it and it sounds like it's appropriate, then that's gives you an idea that it is a weak base. So then once you knew it was a weak base, Stacy, how did you answer the rest of it?
You do the ICE table to find X, and you would get the concentration of the OH value, and then you would get POH, and then you would subtract the POH from 14 to get the pH.
Extremely clearly described. Couldn't have said it better myself. So in this case, do we use Ka or Kb? Which one of those seems to be the best option? Let's not click that in. Can we get an answer from Kat maybe? Which would you use Ka or Kb in your calculations here?
Would we use Kb because it's a weak base?
Fantastic.
And
you're getting
you're going to get your POH out of that, and then you'd subtract 14 minus your POH and you'd get a pH.
Fantastic. So we're probably not going to be able to just look up the Kb value for citrate. We'd probably get the Ka of citric acid, and we'd have to convert that into the Kb in order to answer that question. So we're pretty much out of time. I do have a few more questions that are related to either buffers and how you calculate the pH change, or I have one question related to finding, converting between delta G, K, and E cell. Maybe should we take a vote as far as which one we do next? Should we do the E cell? Let's do number 1 for E cell, K, and delta G calculations. Or let's do a 2 for some of the buffer calculations. Can you just hold up your fingers? 1 for E cell, delta G, K, 2 for buffer type calculations. We see It's almost a 50-50 mix of the hands that I can actually see. We have a clicked in response 2 from 1. I think we're literally split down the middle. The delta G question will probably be quicker, so let's do that one, and then you're welcome to stay on as long as you'd like. I think these are actually a series of 3 of them. I think it's this question here. Okay, so let's say that you're given an E cell reaction at standard conditions, and we know that it has 0.58. Wow, that's terrible. Volts. Include your units, people. Always include your units. Although I was told that my Google form did not accept a unit for the first question, so that's on me. But the second question, that's on you guys. All right. So we have 0.548 volts is our electrochemical potential of the cell. 3 electrons are transferred each time the reaction runs. What do we know about our equilibrium constant K? And this is not one where we start plugging it into a calculator. This is one where we know trends and we answer based off of trends. You want to breakout room for a second? Or do you want to, okay. A lot of shaking heads. We only have 4 responses though, so you got to give me a response. And our responses are almost equal between all 3 of the answers. So Aislinn, can you talk us through how you would answer this question?
Yeah, so since we know that the E cell is 0.548, that means that the delta G would be negative.
Why? What's the basic reasoning for that? You don't have to go into calculations.
The sign of E cell and delta G are always opposite.
Fantastic, nice and simple, straight to the point.
So then, since I know that delta G is negative, that means the reaction would be more reactant favored, so the equilibrium or the K value would be less than 1. So it'd be closer to the reactant side.
Wait,
And
say again. So what is the sign of our delta G?
It's negative.
Delta G naught
Oh wait, no,
is,
it's the other way.
delta G is negative, which means it's product or reactant favored.
Product favored.
Okay, so if we do a Gibbs free energy diagram, here's 100% products, here's 0% products or 100% reactants. Where is the minimum going to lie for this reaction? To the right or to the left?
To the right.
So we're going to have a product favored reaction, and our K is going to favor more products. It's kind of a way of looking at that.
Yeah.
So I just put in this compare to 0, compare to 1, just to kind of like, what do we even compare it to? So for K, our most important thing to keep in mind is this concentration of products over reactants. So that means that if we are thinking about where is K, it's going to always be compared to 1. And so this question was kind of crappy because it says, is it going to be between 0 and 1 or less than 0? But this one, the gist is K is going to be significantly greater than 1. It's going to be off on the right side there. Okay. And so that's answer C. And thinking about the Gibbs free energy diagram, I hope helps with where that is.
Did you
So
say
then what about,
one?
go ahead.
Did you say it was greater than 1?
Correct. It's going to be highly product favored.
I think on there it said less than 1, but.
The answer that I submitted?
Yeah, it was like weird.
None of those
Oh, did I have, oh, is it like this where both of the answers say the same thing?
I just know it said that it was less than 1. So I was confused.
Why didn't someone be like, those are the same answer, silly?
I was confused from the get-go because I couldn't find the answer.
Let's do that. How does that sound? Well, you should yell at me then. Leave it to my last night to make like really crucial mistakes. Okay, does this work then? Kind of, sort of. It works. So for delta G, I guess this kind of is Aislinn's question or Aislenn's description, she actually went through this first to then answer the second part of the question. So
Sorry.
Aislenn said that a positive sign on E cell means a negative sign on delta G naught, because our relationship is delta G naught equals minus NF E cell. So that sign inverts. If it's a positive E cell, it's a negative delta G naught. Remember, both of these are at standard conditions. All right, so I guess this question is kind of useless then. And I think that my last question might also be useless then. Let's see if it is useless or not. No, it's not useless. It's actually a good question. So let's say we've been talking about standard conditions for the last two questions. What is the value of our delta G if we're at non-standard conditions, specifically the conditions that I've listed here, with a Q value of 5.9 times 10 to the negative 8? So is delta G going to be bigger or smaller than delta G naught? Or the same? Couple more seconds. And we're almost at a 50-50 mix. Would anyone like to try to explain how you'd answer this question? Amber, would you like to give it a try?
Sure. Well, kind of like what we just said, if E cell is positive, you'll have a negative delta G naught, and it's going to be, well, hang on. But we also know well, hang on, I just confused myself.
So keep in mind that both of these are at standard conditions. What is our Q value at standard conditions?
1.
Okay. And so now we're saying, okay, well, we have a Q that's 5.9 times 10 to the negative 8. So does that mean that we have more products or more reactants compared to what we had as standard conditions?
We have more reactants.
Okay, so if I draw these Gibbs free energy diagrams that I love, right, we said that the minimum lies to the right. So it is a product favored reaction. Product, that was terrible, I can't write. This is our delta G. So when we were at standard conditions, we were right here on that Gibbs free energy diagram. We had a Q equal to 1. Where's our Q now? Is it further to the left or further to the right?
Maybe to the left.
Like way up here, right? So this Q value here is way up top. So that means that it has much, much further to go to get to K. And it is going to be, I guess you could say, is going to be much, I guess it depends on how you answer this question, right? Are we talking about magnitude smaller or more negative? So I guess the way that's written is more negative. So that means that it would be more negative of a value. So if we calculate our delta G naught of 10, negative 10 kilojoules per mole, maybe this would be negative 40 kilojoules per mole, or something like that. Does that make sense? So this would probably be a calculation type question, but I want you thinking about where is the minimum that the reaction had to go to the right from Q of 1, and that we're going further in that same extreme. So the sign is going to stay the same, but the magnitude of the number is going to get a lot more significant.
Can you clarify real quick whether that would be A or C?
So the way that I would define it is a number further negative, I would define that as C. The magnitude of it is larger, but it is in a negative direction. So I would say that that is the larger, more positive number would be delta G naught. Okay, should we do some buffer problems? Feel free to go whenever you want. I'm just here to help kind of run through some problems. So I think we were, where were we?
I have a question real quick.
Sure.
Is there any way we're going to be able to see what we got wrong on the last 2 exams?
The last 2, you should be able to see that already on exam 2. Is that not the case?
Let me check.
So I think that should be available.
On
And
exam 2, yeah. Oh, well, that one hasn't closed yet, has it?
exam 3?
Yeah.
Correct. Some people are still going to take exam 3 this evening.
Okay.
And so it will release your exam information at midnight tonight.
Okay.
So everyone has to complete exam 3 by midnight. And then as soon as that's done, it will allow you to go back and look at exactly what you did, show you the right answer and the tutorial kind of steps of how to do that, just like your homework normally does.
Okay. Cool. Thank you.
Okay. So shall we do a breakout room for this? Thumbs up for breakout room, thumbs down for no breakout room. No, don't need breakout rooms. A lot of thumbs down. Okay.
Come on, guys. What does that say about us?
I mean, if you want to do it, then yeah.
This is my last chance to do it.
I don't care that much.
Then do it. Our breakout room has just been a little messy tonight.
Yeah, that would be on me. My Wi-Fi is acting a bit crazy today.
It's all good.
By the way, as I have a few of you left, there are course evaluations. Have you received emails about completing those in Blackboard? So please do that. It does give us valuable information about what we need to do to improve and what's going well in our classes. All right, we have 2 clicker responses to this question. How do we approach solving this question? Sure you don't want to do breakout rooms? Pretty confident we know how to answer this, or? So do you want to talk through what each of the approaches would mean? I'll say that from looking at the results, we're not confident in this. But we have a small enough group we can talk through this. We do have office hours over the next few days, so if you wanted to work on any of these topics, please do come spend time with me, or if you can't make any of the ones I have, email me and we can set up another time. So how are we thinking about this? Can we just use a Henderson-Hasselbalch equation, plug in those numbers in the PK? Why not, Amber?
Because I don't really know why, but you do need to use the ICF table first.
Why?
We have to get rid of the sodium hydroxide before we can do the Henderson-Hasselbalch.
For once in my life, I'm going to yell with caps. I hate yelling in caps. But if you ever see a strong acid or a strong base in a mixture, that always has to get used up first. So we have to do a limiting reagent calculation first. If we just try to do Henderson-Hasselbalch with our 2 solutions, which we can tell hopefully mysteric acid and calcium mysterate, 8 means a negative charge. So we do have a buffer, but then to that we're adding a strong base. So the only thing that makes this a little bit tricky is we don't necessarily have the calculations yet to know whether afterwards we end up with a buffer or we end up with a weak acid. So this one is if we have a weak only in the end, we are the equivalence point, right? We've used up all of one of them. So we only have the weak acid or the weak base in the conjugate pair. The second one is if we still have a buffer after you figure out what your limiting reagent is. And the third one is if we use up all buffer gone. Sorry, I'm not speaking English. So if the buffer is gone afterwards and we only have a strong left. So in this one, can we eyeball it? Do we think we're going to have a weak afterwards? Do you think we're at the equivalence point? Do you think we're going to have a mixture? Do you think we're only going to have a strong left? Is it possible to guess? So I'll venture to say we're going to have a buffer afterwards. And the reason I think that is 1.5 millimoles of sodium hydroxide. It's an amount, it's a relatively small amount. And these amounts of our acid and of our base are 965 millimoles in 1 liter, and we have more than a liter. So that means we have more than 965 millimoles of a weak base, a weak acid. The weak base reacts with our weak acid, and we have more than 965 millimoles of these, and we have 1.5 millimoles of this. You kind of see where I'm going there? So we could do the calculation if we had to answer this numerically, but if we just said which approach are we going to use, I would probably bet a lot of money on the fact that we can find out how much of the weak acid sodium hydroxide uses up. All of that's converted to the conjugate base. And then now we say, well, what's our mixture of conjugate acid base? That's our new buffer. Any questions on how I talked through that? If we used up all of this mysteric acid, then we would have to decide, is there any excess base afterwards, strong base, or is it just the conjugate base that's left afterwards? So I would answer this one as, what is that, D? All right. That doesn't really make sense there. Why is that? What's going on here? Oh, that's because there's a different problem there. Okay. And these are the types of problems I'm happy to make up all day if we meet at office hours. Is anyone thinking about coming to office hours tomorrow? Which time?
What times are there?
That's a very good question. Tomorrow office hours are at 10 to about 11:30 or 12, and then at 8 p.m. until about 9:30ish. One of those 2 times work for y'all?
I could probably go to both.
Okay, you're welcome at both. So I think everyone can probably turn off their mutes if they want, just have a conversation about how we approach this. I'd love to hear thoughts on what you see here and how we approach it.
Well, hydrochloric acid is a strong acid, so we know we have to use all of that up first. So you can't just use the Henderson acid.
So Verda, it's a little hard to hear you. I think I'm going to repeat what I think I heard you say, that you said HCl is a strong acid, so we're going to have to use all of that up. And then what did you say after that?
I said, so that means that you can't do B because you're trying to use up all of the strong acids first.
You can't what?
You can't use the Henderson-Hasselbalch equation yet.
Great. And so I think there's an extra thing said in there, it needs to be said. We're at the equivalence point. So that means by definition that we have used up all of our strong acid with all of a base. And so lithium formate in this problem is a base. How do we know that it's a base?
Because there's formic acid.
Great. So formic acid is a pretty common acid, and formate is the conjugate base of that. And the lithium means it's a salt. Lithium goes in water, spectator ion. Formate is a weak base. So we have a strong acid, weak base, and the definition of equivalence point means that we had just enough of both to use each other up, and so they're all gone afterwards. So then what are we left with in solution afterwards? Is there nothing? Is it pH 7 after we're done?
No.
What is there?
Well, if it's a strong acid, is it going to be really small? Like small?
So we said we have a strong acid and we have a conjugate base, and they're going to react completely, right? So what do we have after the reaction's done? What's that?
Would it be a salt?
In this case, it's not necessarily a salt in the way you think about it, because we left out lithium ions, chloride ions that are also there as well. So we have lithium chloride.
So
Do
is
we have, go ahead, Sydney.
is it 7 because it's a equivalent point? Or but it's not a, never mind.
Well, you get another acid and a base. I mean, it will add up to be HA, but if you're looking at your hydrochloric acid, it'll be formic acid, and then it'll be lithium chloride. Or
Fantastic. So this is, we made formic acid in the process. So every single conjugate base, right, that we started with, every single formate was forced to take on an H+ ion. And all of it, remember, this is a one-sided arrow. This is a complete reaction if you have a strong in there. So then after the reaction's done, all we have left is formic acid. That's it. So how do we find the pH of a solution that is only formic acid? Which of these approaches is appropriate? Do we do the Henderson-Hasselbalch equation? Do we do an ice table? If so, what steps do we use? Do we just take the concentration? Because we'll have 59.8 millimoles of formic acid afterwards, right? Do we just take negative log of the concentration of that formic acid in solution? Amber, you're nodding your head, yes. Why is that the best approach?
Not sure.
is it because you're using a strong acid?
So if I just, out of context, if I just say, okay, we're going to take the negative log of the concentration of formic acid to find the pH, does that sound right? Kat's shaking her head. Why not?
I don't think that that's one of the strong acids, and you only do that if you have a strong acid. You only take the negative log of it. So I don't think you could do that.
So then how do we find the pH when we have just a weak acid in water?
You'd have to use an ice table, and if you're using an acid, then you'll just take the negative log of C.
Because your ice table, the X is?
You end up with a hydronium ion.
Great. So I think where people get stuck in this a lot is they think about the whole process and there's multiple steps, and they say, how do I take the negative, or how do I find the pH in multiple steps? That's not what I want you to think about. What I want you to think about is what has to happen and can't go backwards. So in that case, that's the full headed arrow. You can't think about anything else until that reaction of a strong has been neutralized. Once that's done, then you stop and say, what do I have? Is it a mixture? Is it just one thing? Is it an acid? Is it a base? Is it strong? Is it weak? And once you've done that, then you go back to the original stuff we talked about. So if I just said in a completely different context earlier, right? We have a weak acid in water. How do you find the pH? We do an ice table and we take the negative log of the concentration of H3O plus. If I have a weak base in water, then we do answer E. If you have a buffer, then we do Henderson-Hasselbalch, right? So the question is, after the complete neutralization reaction is done, what do we have? And once you do that, then you know how to answer that question. But if you don't identify what it is, then you can kind of keep spinning your wheels. So the last question related to that is, let me go ahead and answer that question there. When we use an ice table at the equivalence point for this titration, are we going to end up using Ka or Kb to do our ice table?
Don't we have to like use the KB to find the Ka?
If we only have the Kb, we can use the Kb to find the Ka. You're saying in this case because we started with the base? Is that what you're saying? So possibly, it depends, but what you've probably noticed from going to the reference section in OWL is that if we're starting with a conjugate base, like lithium formate, it's kind of the definition is formic acid is an acid, and lithium formate gives us the conjugate base, as opposed to if we had a base like ammonia, that's like a base for base's sake, and formate is really the conjugate base of a weak acid. So it's a little bit semantics, but if you were to go and look for the Kb of lithium formate, you're probably not going to find it. But you would be really easily able to find the Ka of formic acid. Does that make sense? Am I confusing you? Yes, on both.
No, it's good. Thank you.
So the question is, at the end when we do this ice table, are we going to be using Ka or Kb? And it looks like most people are saying Ka. Why is that?
Is HCl is such a common strong acid that we just know the Ka of it.
So we actually don't know the Ka because Ka is like infinity on HCl. Well, we have more than 95% released. So we don't even talk about Kas for most of the strong acids. So if we're talking about an ice table, the ice table we're going to be talking about is formic acid. Let me write it at the top here. So formic acid is HCOOH. So when we started this reaction, before the neutralization happened, what we had in water was HCOO minus. That was all forced to take a proton on by HCl. So after that neutralization reaction is done and we've hit the equivalence point, we have 0 more HCl. It's all gone, all been used up. And all of it has made now this HCOOH, that formic acid. So then the question is, how much H plus or H3O plus is released when that's allowed to just relax and equilibrate in water? And so that's our Ka. So the Ka for formic acid is what we're going to use in the ice table to calculate our concentration of H3O plus, or X, and then we're just going to take the negative log of that once we've gotten to that point. Okay, so that is what I have prepared for tonight. I know it's more than you might have bargained on, but hopefully that was useful, at least in giving you some ideas of what are the things you might want to study, the questions you want to bring to office hours, and maybe some of the cleared up some confusion you might have had in some of the topics. So I'm going to go ahead and close out my shared screen and click in Ka there. I'm happy to stick around for a few more minutes if anyone has some more questions, but I imagine y'all are probably done after an hour and 45 with chemistry tonight. And Kat, I know that you got a big night ahead of you, so
Yes, I do.
hopefully this will help with some of those problems you're going to be working through. So does anyone have questions? I'm happy to stick around.
Hey, Dr. Bailey, quick question.